Hi, hello. This is Federico Cappuzzo from Siemens Digital Industry Software. I would like to welcome you to the presentation of the paper System Simulation for Autonomous UAV Design. I had a chance to co-author this paper with Kenedy Matiasso Portella, a former intern at Siemens, Jean-Patrick Mascomère from Total, Raphaël Lallement from Scalion, and Guillaume Thalmann from Altran, so other partners of the Comfort Drone Research Project. This is an overview of the agenda. I will discuss the motivations of the study, we'll briefly describe the tools used, and I will go through the use case of the modeling of an octocopter for oil and gas exploration, which is the use case 3 demo 1 of the Comfort Drone project. And so I will show how we model the drone, the simulation results obtained, and then how was it possible to establish a co-simulation framework for heterogeneous fleet modeling. And then I will draw some conclusions. So what are the motivations that led to this study? As we know, UAVs are industrial disruptors. They can benefit different industries. They can improve work efficiency and reduce costs and risk of the activities they perform. And as for any other product, UAVs must meet some mission requirements. Now, as UAVs can operate over a broad spectrum of activities, it could be interesting to develop a UAV platform that just by providing some minor modification, software or hardware, can be quickly adapted to perform these different missions. On top of that, in order to reduce the time to market and improve the product quality, requirements should be verified already during the development of the UAV. And this is where system simulation can provide some key advantages, in that system simulation models can help explore the design space, providing trade-offs between different variants of drones. It can complement and sometimes completely replace expensive physical tests. And then system simulation it allows to create high fidelity models that can be used to develop guidance, navigation, and control algorithms with co-simulations in the early phases of the development. But then as the design matures, it's possible to export system simulation model to software in the loop and hardware in the loop platforms. So these models need to be real-time compatible, right? So it is possible to verify and validate the behavior of the controllers with more sophisticated techniques, where also the limitation in computational power can be taken into account. So why do we think that system simulation is particularly suitable for UAVs? Well, UAVs are complex multi-physical dynamic systems. Even if you think about the simplest UAV out there, well, there are several subsystems with different physical domains interconnected. Think about the energy storage in the battery, how electrical energy is converted into mechanical by the electromotors, the propeller and the aerodynamics, and it is of course a dynamic system in that its state variables change over time. So system simulation provides the right set of tools to model these kind of system, and of course when you can model it clearly, you can clearly simulate, analyze, and optimize the UAV performance. On top of that, you can create high-fidelity models for continuous guidance navigation algorithms development. The tool used in this study for system simulation activities was Simcenter Amesim. It is a software tool dedicated to the modeling and simulation of dynamic multi-physical systems. It provides several libraries that cover different physical domains like fluids, thermodynamics, mechanical, electrical, and some libraries dedicated to application domains like propulsion, and so on. It is also an open mechatronics simulation platform, open in the sense that it provides interfaces dedicated to particular pieces of software like MATLAB Simulink, and then also complies with some standards like the functional mockup interface, which are standards developed so that different tools can communicate with each other. It also, as said before, it supports real-time platforms for software and hardware-in-the-loop simulations. Now, let's discuss about the use case of the modeling of an octocopter for oil and gas exploration. We received some specifications from the partners about the UAV type, so an octocopter with coaxial propellers. We had the reference about the electric motor and the propellers used to build the drone, the kind of battery and the nominal voltage. We also knew the maximum takeoff weight, the payload, and the desired autonomy. Note that during the mission, the drone is supposed to drop some darts or seismic sensors to perform oil and gas exploration. It means that the inertia of the drone can vary quite abruptly during the mission. I will now go through the modeling and validation possible of the different subsystems of the drone. Let's start with the electric motor. So we had the reference of the motor chosen for the UAV just presented. So we went to the on the manufacturer website where we could retrieve some main specification and the performance curves. We then created the model. You can see a screenshot of it on the left, where the electric motor, well, we tried to reproduce basically the test described by the manufacturer. So the electric motor, you can see here, was connected to a torque source. Also the velocity speed was known, and then the voltage applied to the motor is controlled by the motor controllers. So we now compare the results simulated with the supplier datasheet. So we see, as explained before, that the rotational speed was imposed, so there is no surprise that the two lines are superposed. And we also see that the efficiency simulated with respect to the one provided by the datasheet is pretty much the same. Also the power, it looks the same. However, it is surprising to see that the current, well, there's a sort of gap in the current simulated with respect to those provided by the manufacturer. We cannot really explain this inconsistency because, as we can see, the power and the efficiency are exactly the same. So we really expected also the current to be in agreement with the data provided by the supplier. Next, we modeled the performance of the propeller. We used an extended blade element momentum theory extended to the counter-rotating propeller configuration used by this octocopter. And we validated the simulation result with some experimental results of a very similar propeller that we have found in a previous publication. So here we provide the comparison, and we consider the results as acceptable. For what concerns the battery pack modeling, we use a dedicated Amesim module for the battery precising, and we provided three targets, namely the voltage, 48 volt, which is the rated value, the power, and the energy obtained with a previous simulation where the mission of the drone was simulated just with an ideal power source, so that we could estimate at the end of the mission what was the overall power consumed and the energy by integrating the information power. So by providing these three targets and using the battery database available in Amesim of different polymer lithium technologies, the module, the battery pre-sizing tool module, compute the battery architecture, the cell nominal capacity, but also different tables to describe the open circuit voltage variation with respect to the state of charge of the battery, the charge and discharge ohmic resistance with respect to the state of charge. However, it was not possible to include the dependency of these variables with the temperature of the battery because we did not have this data, but it is possible to include it in a second time. For what concerns the modeling of the electrical loads other than the electric motors, such as communication systems, controllers, and other power electronic losses, we imposed a constant power consumption, which is roughly about 20% of the nominal power. For what concerns the controllers of the propeller's rotational speed that in turn control the UAV altitude and altitude, we used a component available in the signal library of Amesim, which is based on the internal model control principle, which is represented here on the bottom of the slide. It is particularly suitable for this kind of application because it combines an internal model of the system with a control shaped for specific response type. Its calibration is quite easy because it's limited to providing some physical parameters of the simplified model, in particular the inertia on the different axes of rotation and the mass of the drone. And finally, this is the flight dynamics. The UAV dynamics is modeled with a rigid body with 6 degrees of freedom and variable inertia. The aerodynamics is modeled in a very simple way. We have just a constant drag coefficient representative of a flat plate positioned perpendicularly to the flow and a reference surface of 1 square meter, which is representative of the drone's wet surface. The inertia of the UAV were deduced by a CAD that was built according to the specifications provided by the partners, so give some estimation of the real inertia, the real mass distribution of the UAV. So let's have a look at the simulation results. This is the mission that was simulated. The drone takes off, it cruises for 1 kilometer, and then it starts dropping the seismic sensors. There are 6 of them, and each drop event is represented by a blue star. And then it goes back to the base and lands. The inputs provided to the drone for the simulation are its positions, so namely the altitude, longitudinal and lateral position, and the yaw. The controllers that we have seen before modulate the rotational speed of the propellers to control the attitude in terms of pitch and roll of the drone in order to orientate the thrust vector so that these positions are followed. So here we have decomposed the mission on the position and attitude, and we have plotted the target with the blue color and the simulated result with the red color against time. We can see that the altitude, longitudinal and lateral positions are correctly followed by the drone. The red line is superposed basically to the blue line. And here on the bottom row of these subplots, we see the roll, yaw and pitch angles of the drone. So as I said before, the roll and pitch vary during the mission so that the longitudinal and lateral positions are followed. And you can see that we also imposed the yaw to the yaw angle to be 0 throughout the whole mission. So the conclusion from these results is that the UAV can follow the trajectory and complete the mission, so the subsystems are sized correctly. The final part of the use case consisted in the creation of a co-simulation framework for heterogeneous fleet modeling. And this framework consists in coupling Simcenter Amesim and the model we have just described with MATLAB Simulink, which implements the guidance and control algorithms, with Simcenter Prescan. And this is another Siemens tool which provides sensor modeling capabilities, so those sensors needed for the UAV navigation, like LiDARs, radars and cameras and so on. And then the environment modeling capabilities, for instance, a urban environment with buildings and open spaces where the UAV is supposed to operate. So how it works? Simcenter Amesim computes the drone state variables like positions and attitude. It communicates them to MATLAB Simulink that receives also from Prescan the sensor's output. These informations are combined from the control algorithms, and then the control input is provided to the Amesim model, and also the drone states computed by Amesim are passed to the Prescan model, which is able to correctly position the sensors. Prescan also provide excellent visualization capabilities that help the user understand how the mission is executed. Here there is an example of a detect and avoidance maneuver. So we have a drone that is flying simply from a point A to a point B. You have here the video on the left, and on the right you see the upper view of the scene. So during the trajectory, which is supposed to be a straight line, we placed a building in the middle. So as you have just seen, the UAV is able to detect its presence and fly around it. We implemented an optimized artificial potential field algorithm. So the obstacle has represented by a charge that repulses the drone, and the sensor used it is an ideal sensor. The second scenario that we simulated, it is that of a cluster flight. So there are 4 drones that takes off at different positions and is supposed to reach a common target position without touching each other and collide with each other during the flight. Here we implemented a modified version of the artificial potential field. The sensors again that have been used were ideal, and also we made an assumption such as that all the drones' position are known. So the drone communicate with each other, and they all know each other's position. So what are the conclusions? First of all, we have been able to create an integrated performance model of the UAV. The motors and the propeller's performance compared favorably against data that we have found in the manufacturer website or open literature. And we know that this model can help verify the mission requirements during the development of the drone itself. Mission requirements, of course, in terms of performance, like the autonomy, if there is enough thrust provided by the propellers and the propulsion system, and so on. We proposed a co-simulation framework for the design of autonomous UAVs that can also be used for heterogeneous fleet modeling. And this framework can be used to perform trades on the UAV sensing capabilities and GNC algorithms. Again, it combines a high-fidelity model created with Simcenter Amesim with advanced sensors, navigation sensors capabilities, and these can be used again to for a continuous development of guidance navigation and control algorithms. What is the further work that we foresee? First of all, we are currently validating the octocopter performance with experimental data, so flight test data. We also foresee the use of physics-based navigation sensors instead of the ideal ones used in the two scenarios presented before. And also we want to perform software-in-the-loop and hardware-in-the-loop simulations to analyze the control algorithms and embedded processors. I would like to thank you all, and I'm open to take any questions. Thank you.